this video, we're going to talk about two-dimensional arrays. We've already learned about single-dimensional arrays, which allow us to store a list of items. A two-dimensional array is somewhat different in that it allows us to store a two-dimensional collection of values. In other words, something that we might picture as rows and columns, sort of like a spreadsheet. We're going to learn that a lot of the syntax and concepts related to two-dimensional arrays are things that we also learned about in single-dimensional arrays, and we'll just be extending the ideas. When we stored information in a single-dimensional array, we selected a single identifier to represent that collection. We'll do the same thing with two-dimensional arrays and select a single identifier that will represent the entire collection of information, everything in all the rows and columns. We learned that the items in a single-dimensional array have to have the same data type, and this is also true of data values that are in a two-dimensional array. Finally, we learned that when we're creating a single-dimensional array, the size is fixed and it's difficult to change. This will also be true with a two-dimensional array. Once we set the number of rows and columns, we won't be able to adjust these easily. Let's think of some examples of why we might want to create a two-dimensional array or table of information in a program. Suppose that you wanted to store the quiz scores for all of the students in a particular course, like Computer Science 220. You might have 3 different students, and each student might have 5 different quiz scores. In this case, it might be easy to picture the information in a table, something that had 3 rows, 1 row for each student, and 5 columns, 1 column for each quiz score. You could also imagine a situation where you might be storing information about temperatures. Suppose that you want to store the temperature reading for every day in a 2-week period. You might create a sequence of rows where there's 2 rows, 1 for each week, and then within each row you have 7 columns, 1 for each day of the week. Let's look at these situations more carefully. First, let's think about the quiz score situation where we have a series of students in a course. Perhaps we have 3 students in a course, and perhaps we have 5 different quiz score values for each student. In this case, we might want to create a table of information. I'm going to draw the table in Microsoft Word here, where we have 5 columns, 1 for each data value, and we have 3 rows, 1 for each student. So we might be creating a collection that looks somewhat like this, again, where each of the rows in the tables represents one of the students, student 1, 2, and 3. And then each of the columns in the table represents one of the quiz scores. So this might be quiz number 1, quiz number 2, quiz number 3, quiz number 4, quiz number 5, where we're storing the 3 students' scores, 1 score per student per quiz. If we wanted to create that type of collection, the declaration for that in Java would look like this. You can see that it has a lot of similarities to declaring a single-dimensional array. Just like a single-dimensional array, we'll start out by identifying the data type of the information in each of the boxes. Remember, each box represents 1 quiz score. If we wanted to store integer quiz scores, we would put int as our data type for the collection. Then, because our collection has 2 different dimensions, we're going to put in 2 sets of square brackets. Next, we're going to select an identifier for our collection. In this case, I'm calling it quiz score. And then finally, we have to request the space to be allocated for our program. We're going to say new, that's the reserved word that requests the space. And then we're telling the computer that we want to make integer-sized spaces and that we want this many rows and columns of them. The first item here is always the number of rows, and the second item in square brackets is the number of columns. Because we said we wanted to have 3 rows, I would set a variable equal to 3 that I can use in that first position, and then set a second variable that I can set equal to 5 and use that in the second position. If you wanted to use literal values here, that would be completely fine as well. So we could put in the literal value 3 and the literal value 5 to indicate that we want 3 rows and 5 columns. Using the named constants allows your program to be a little bit more flexible, so that, say, you change the number of students in the class and a few people add, so now you have maybe 20 students in the class, you could easily update your program so that it's storing 20 rows of data instead of just the 3. And of course, that would change the amount of space that was stored in the memory of the computer. But once you have the memory set up, once you've made your declaration statement where you request the space, it's hard to change the amount of space allocated to your table after that point. So be sure to think through what makes sense for the number of rows and columns for your program. If you're not 100% sure how many rows or columns your program should have, take an educated guess and remember to be generous with your guess. Make it a little bit larger than you imagine you will actually use. Let's look at another example of declaring a two-dimensional array. Let's look at our temperature situation. So remember, we were thinking perhaps we would want to store a table of data where each box in the table represents a temperature value. Maybe it's a reading that we're taking from an experiment, or maybe it's the outdoor temperature for that day. In any event, if we want to store temperature values, temperature readings across 7 days of the week and a 2-week period, we'd want to create an array that has 2 rows and 7 columns. I'm going to draw that in here again with Microsoft Word. So I want to have 7 columns and 2 different rows. Visually, my data that I'm storing, I'm imagining is going to look something like this, where each box represents a different temperature value. And remember that when we had single dimensional arrays, we could specify all of the array values, all of the individual element values that would be part of an array. We can do that with a two-dimensional array as well. We'd use syntax like this, where we say the data type of each box. If I'm trying to store temperature values that are decimals, I'd put double as my data type. Then I'm going to put the 2 sets of square brackets. That indicates that I'm using a table of information, something that has rows and columns. Then I need to pick my identifier for the collection. I'm picking the identifier temperature. And now, rather than requesting empty space, I'm going to tell Java exactly what data values I want to store in my table. I'm going to do that with a set of nested curly brackets. Note that the outside set of curly brackets here represents the entire collection, and then each row in the table is also delimited by curly brackets. And when Java sees this kind of declaration, it knows to take the data values in order and use those to fill in the table. So I'd fill in 32.4, 55.6, 76.2, 80.9, 40.0, 51.1, and 50.0 in my first row of the table. That's because that's the information in the first set of curly brackets. Then I use a comma to separate the individual rows in the table. And now I'm listing out all the data values in the second row. That would be 51 or 56.1, 60.3, 77.2, 34.5, 40.2, 55.1, and 60.0. So just like a single dimensional array, we can either specify all of the data values, or we can request empty space to be allocated to our program for our two-dimensional arrays. Now, you might be wondering how we could access the individual elements that are part of our collection. As Java's thinking about these data values, it thinks of the indices for them sort of in a similar way that we thought about them with single dimensional arrays. It always starts counting the indices at 0. So this table here would have columns 0, 1, 2, 3, 4, 5, and 6 for our 7 rows in the table. I don't know if I'm going to be able to squeeze in some indices for the rows here. This first row would be row 0, and the second row would be row number 1. Maybe I'll take the space on this top table to fill in the indexes that would represent each of these individual spaces in the table. So this top one would be row 0, column 0. This next one would be row 0, column 1. Next one would be row 0, column 2. Row 0, column 3. And then finally row 0, column 4. The next row would be row 1, column 0. Then row 1, column 1. Row 1, column 2. Row 1, column 3. And row 1, column 4. And then finally, you get the idea. Next one is row 2, column 0, row 2, column 1, row 2, column 2, row 2, column 3, and row 2, column 4. This is just a visual of which element is in each of these kind of conceptual boxes in this table. Remember that the actual information that would be stored inside this table would represent quiz scores, not indices, but I'm showing you the intersection of the row and the column, so you can think about how you would access that particular location in the table. As we were just talking about, if we want to access an individual element in the two-dimensional array, we have to specify both the row and column that we want to access. So you're going to need to indicate two different index values, a row index and a column index, and that will allow you to access a single value in the table. For example, if we said, I want to access the quiz score table at index 0, 1, that would mean row 0, column 1. I want to change that value to be 7. Getting back at our table, finding the intersection of those row 0, column 1, be changing this value to be a 7. If I said something like temperature is temperature weekday, I would get the data value for week and the data value for day. Let's say 1 and day was 3. So that's saying in the second week, the one that's labeled 1, on day 3, which would be Sunday is 0, Monday is 1, Tuesday is 2, Wednesday is 3. So it would be Wednesday of the second week. Again, looking at our table, we'd be going to row 1 and then column 3. The data value there would be the 34.5. That would be what we were printing here when we say temperature is.